Hello, class. We are now going to discuss the reactivities of aldehydes and ketones. Now this here on the left is our aldehyde, and it has a piece in that functional group called a carbonyl. And so does the ketone. Both has a carbonyl. Now, what is the major difference between an aldehyde and a ketone? Well, an aldehyde has a hydrogen that's directly attached to the carbonyl carbon. And so because that's a hydrogen attached to a carbon, when let's draw an aldehyde here, I could draw it like that. That is an aldehyde because there is a hydrogen right here that I'm not drawing in. So be very cautious when you're looking for aldehydes in molecules that the hydrogen may not be shown. But if I take this and turn that into a carbon and turn it into a CH3, I now have a ketone. Now, ketones and aldehydes are very, very important in biology. Because they're in a lot of molecules that are really, really important. There's ketones, there's carbonyl compounds in our DNA. There's aldehydes and ketones in hormones like testosterone and what's the other one called? Progesterone. That's another example. But we can, from a lab perspective, we can look at simple aldehydes and simple ketones. Like this guy right there, that is a aldehyde, and it's the most simplest aldehyde, and that's called formaldehyde. Formaldehyde is the molecule that we use to embalm bodies with. It's a molecule that preserves tissue for a really long time. As an undergraduate, I was in a chemistry class, and the professor brought out a jar with a fetus in it. And the baby was born in the 1970s, and it's been in this jar for 20, 30 years and still in pristine condition. It's a very powerful preserving agent. The most simple ketone that we use all the time in labs, right there, is acetone. We can use acetone in reactions. We can use acetone as a solvent. We can use acetone a lot of times in labs. It's just a solvent to clean your glassware. It cleans your glassware very well and evaporates really fast. So that's a good use for acetone. Let's see here. This one's just fun. What we have here is benzaldehyde. Okay. So that's benzaldehyde, which is an aldehyde, and it's the molecule that's responsible for vanilla flavoring. Well, you don't have to memorize that, hey, benzaldehyde is vanilla flavoring. No, it's just an interesting fact that we can relate to these molecules that we're talking about, that we've seen them in one way or another in life. Either the hormones in our body has these ketones and aldehydes, or the flavorings or the smells that we encounter. So I think it's just fun and there's many other common molecules that we're aware of that have aldehydes and ketones in them. And the textbook shows you many of those examples, which is just fun to know. So that's the introduction to some common aldehydes and ketones. Now we want to discuss the nomenclature. How do we name aldehydes and ketones? Well, there's 4 general steps that you need to take. And I'm not going to write them on the board, I'll just talk about them. Step 1, you need to identify and name the parent chain. That's the same for naming all molecules, right? You need to find the largest parent chain. That's step 1. Step 2, you need to identify the substituents on that parent chain, so the side groups. Step 3, assign a locant number to that parent chain. And when you do that, then you are able to put a number associated to the substituents. And then you take all that information and you assemble it in alphabetical order and you come up with the name of the molecule. So let's take a look at that. So if I have this molecule here, what would the parent name be? Well, we count the longest carbon chain, 1, 2, 3, 4. So that would be a butane. All right. But what if we had 4 carbons and it was an aldehyde? Like that. So do you see the longest parent chain here? There's 1, 2, 3, 4 carbons. So the 4, we say butane. But when it's an aldehyde, we cross out the E. Okay, so it's still the butane. And then we replace the E with an Al. So this molecule right here would be called butane. There, I would put an E there, but it's an aldehyde, so I have to put the Al there. Butanol. So let's find the longest parent chain. Now, when you number an aldehyde, you always start with the carbonyl carbon. 1, 2, 3, 4. That's how you would number the substituents. That's how you would name the parent chain. But in this example right here, we don't have any side chains or substituents coming off of carbons 2, 3, or 4. So the name is just butanol. Now if we take another example here, let's see, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbons there, right there. So when we look at that molecule, we need to find the longest carbon chain, right? So is it 1, 2, 3, 4, 5, 6? Or could we find a longer one? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 8 carbons long. So we would call that what? An octane, right? But let's change this up a bit. Okay, so I want to draw it over here. So 2, 3, 4, 5, 6, 7, 8. And then right here, instead of putting a methyl group, let's put a aldehyde. Okay. Now we need to find the longest parent chain. So we could go 1, 2, 3, 4, 5, 6. That's a chain. But can we find a longer one? 1, 2, 3, 4, 5, 6, 7, 8. So I found a chain that's 8 carbons long, and I found one that is 6. Now in this example right here, we would call this an octane because the longest carbon chain is 8. But with this one, we would call this a hexane. And the reason why we call it that is because when we numbered the longest carbon chain, you have to include the carbonyl carbon in the aldehyde. So the longest carbon chain including the carbonyl, is 6. So that's that's the longest chain, okay? Well, remember, we have to drop the E, and the parent name would be hexane. No E, we replace it with the Al. So that right there is the parent name. Now what we have to do is number the parent chain in the proper way. Do you see how I started over here and went 1, 2, all the way to 6? That's not how we're supposed to put the locant number. You have to always start with the carbonyl carbon. So the numbering scheme in the pink and green numbers were just used to figure out the longest carbon chain. Now, I'm going to number it, the longest carbon chain, the proper way, starting with the carbonyl carbon as number 1, 2, 3, 4, 5, and 6. So now that it's numbered correctly here, what are the substituents here? There is a 1, 2, 3. There is a propyl group attached to carbon 2. So how would we name this molecule? Well, we have a propyl group right there on carbon 2. So we would just go 2-propyl hexanal. So that would be the name of that molecule. So let's do another example to make sure we understand the proper numbering scheme when we look at aldehydes, okay? So here's an example of an aldehyde that has an alcohol in it and an alkene. And we'll tackle problems like this a little later, but the purpose of this example is not to name this molecule, it is to number the longest carbon chain in the correct way. So if I number it 1, 2, if I number in that order versus this way, what numbers or what color of numbers is the correct way of numbering this parent chain? And hopefully you've all said in your mind that it would be the blue numbers. Remember, we always start with the aldehyde carbon, and then we number according to like that. So that's the idea about that one right there, okay? Now let's take a look at ketones. So if we have that right there is what? Butane. But if I change that up to something that looks like this, it is now a ketone, the longest carbon chain. 1, 2, 3, 4. So that's still a butane. But when we have a ketone, we drop the E, and then we add this, O-N-E. And we don't pronounce that as the number 1. It's actually pronounced own. So we take that and put that in the place of E, and we go butane own. Another couple ideas that you need to be aware of is when you have stereocenters. So if we number this carbon chain like this, so the longest carbon chain right there is 3, so propane. So we say propane is the parent name, but we see that it is an aldehyde, so we have to drop the E and add the Al. I see a substituent at 2, there's a 2-chloro. And then on carbon 3, we have a phenyl group. Remember, the benzene ring can be called a phenyl as well. So how do we name this? Well, we have to figure out the stereocenter, the configuration, and we will find that that is an R. So that would be an R right here, right? So now how do we put this all together? Well, we look at the substituents, and we have to put them first, but in alphabetical order. And so C comes before P, so we have to designate that the 2-chloro group, that's a stereocenter, so we put it in parentheses, we say it's an R, dash 2 dash chloro. Okay, so that accounts for our chloro group, so that's done. Now we have the 3-phenyl, dash 3-phenyl. And then what's our parent name? Propanal. So that's how you would name that molecule when you see stereocenters. You just stick it with the substituent. Now what about this guy right here? Now this is clearly an aldehyde, but when you have an aldehyde that is directly attached to a ring, we change the name up a little bit. What you have to do, the parent name now becomes carbaldehyde. So carbaldehyde. So that's the parent name there. And that is kind of like the substituent. So we put that name at the beginning. And what is that guy? That is called a there's 6 carbons, hexane, right? So when you have an aldehyde that's attached to a ring, we have this crazy different rule that we call the aldehyde a carbaldehyde. So that right there, in the name, it tells you you have a ring. And then that cyclo also tells you you have a ring. And that hexane tells you how big that ring is that the aldehyde is attached to. So that's another nomenclature rule that you need to be aware of. The IUPAC nomenclature system also recognizes a couple molecules with their common names. So we've seen this one already before. That's called formaldehyde. That's a common name. This is a ketone, which is called acetone. That's a common name. And this one right here is called benzaldehyde. Just another common name. Something that you just have to put to memory and be aware of. What we have here are a list of reactions that you have gone over and learned in Orgo 1. And what they all have in common is the product, how to make aldehydes. And so we need to review this to make sure, because you need to know these reactions. And we're not going to go over them in depth here, but this is a review. So everything here in green right here is from chapter 12. So you can go back into your text and look at that. And another way you can look it up is the oxidation of alcohols, and particularly primary and secondary alcohols. When you oxidize them, what do we get? So in this case, we have a primary alcohol. And if you treat it with PCC, which stands for pyridium chlorochromate, we will oxidize that primary alcohol into an aldehyde. Or you can use DMP, which stands for Des-Martin's oxidation. And if you use that, you get the same product. So that's Des-Martin. Or you can use DMSO and oxalochloride right there in step 1. And then step 2, you add the triethylamine, and then you will also get this aldehyde. So these have some names. Like I said, this is that's the Des-Martin. And this whole thing right here is called the Swern oxidation. So we've got some names here. We have the pyridium chlorochromate, the Des-Martin, and the Swern oxidation. That will take a primary alcohol and convert it into an aldehyde. We have ozonolysis of an alkene. If we treat an alkene with ozone, and then in the second step we treat it with dimethyl sulfide, what happens? It cuts that double bond right in half, adds an oxygen to that double bond to give us our aldehydes. And that is found in chapter 8 of the text. Or if you're looking at a different textbook, you would just look up ozonolysis of alkenes and you will find it in whatever textbook that you are looking at. Now the reaction in pink, what do we have here? We have the hydroboration of terminal alkynes. Terminal is key. And what happens is you see that we have carbons 1, carbons 2. Okay. And what happens is that the oxygen right here goes to carbon 1. So it follows the anti-Markovnikov rule here. And so this reaction right here, you can see generates a aldehyde because it follows, or it is an anti-Markovnikov addition there. And so what chapter is this in? This is in chapter 9.7 of the text, or you would look it up as hydroboration, oxidation of terminal alkynes. So those are the, what is that? 1, 2, 3, 4, 5. That's 5 ways that we can make aldehydes from the reactions that we have learned in Orgo 1. So next, I'm going to show you ways that we've learned in Orgo 1 how to make ketones. So now we have a secondary alcohol. If you take secondary alcohols and treat them with the chromic acid combination right here, it will oxidize that alcohol into a ketone. Or you could use Des-Martin, or you could do Swern oxidation, or you could use PCC to get the same transformation. And all of that information right there can be found in the oxidation of alcohols chapter or chapter 12 in our textbook. We have ozonolysis of alkenes again, but what's different now is now we have 4 R groups in this particular example, and so you can see now we are going to have two ketones. So this is ozonolysis of alkenes, and then in pink, what do we have here? We have the acid catalyzed. Here's the acid, there's the catalyst, and it catalyzes a terminal alkyne into a ketone. Now this reaction right here puts the oxygen atom on that carbon. So if that's carbon 1 and that's carbon 2, it puts it on carbon 2. And now we're seeing that reaction follows the Markovnikov rule. Whereas the previous example, when we were looking at making aldehydes, We did the hydroboration oxidation reaction to put the double bond oxygen on carbon 1, and that's anti-Markovnikov. Isn't that cool? You can select which carbon 1 or carbon 2, to put that carbonyl on, and then that determines if it's a ketone or an aldehyde. But this little section right here is looking at ketone formation. So there's that reaction that is going to also be in chapter 9, or you would just look up acid catalyzed hydration of terminal alkynes. And so that's Orgo 1, but we have learned another reaction in Orgo 2. Remember the Friedel-Crafts acylation? So Friedel-Crafts acylation, that can get us to a ketone as well. So for example, if we have our benzene ring and we treat it with a acid chloride that looks something like this, and we have our Lewis acid, what is that going to do? That's going to give us a compound that looks like this. And that right there is a ketone. So a lot of tools in your organic chemistry synthesis toolbox. Lots of reactions to get us what type of functional groups that we are looking for. In organic chemistry, oftentimes you can predict reactivity based off of using this principle. What we have here is a electron-rich species. I know it's electron-rich because it has lone pairs and it has a formal charge of -1. So this species is electron-rich. Whereas this species right here has a positive charge. So that is electron poor. And more often than not, if you can identify a electron-rich part of the molecule and a electron-poor part of the molecule, those associate with one another, right? Opposites attract. And so we would have a reaction like this, in which our product would then be something that looks like this, right? And so we would have, so what names do we use for these species right here? This would be a nucleophile, because it's nucleus loving, and then this is a electrophile. Electron loving. So nucleophiles and electrophiles react with one another because the nucleophiles are electron rich, electrophiles are electron poor. Now this isn't the case for all reactions, but a lot of reactions in organic chemistry. So if we take this idea and apply it to aldehydes and ketones. So let's look at a ketone right now. Can we identify an electron-rich part of that molecule and an electron-poor part of that molecule? Now we can draw a resonance structure to help us see this. Now when we look at that ketone, do you see now that we have a electrophilic carbon, a carbon that doesn't have a lot of electron density. So it is electron poor. So we can look at this molecule right here and kind of, how does that guy react? And you're like, if I look at our resonance structure, I know there's going to be a partial positive charge on that carbon. So that's a place on the molecule where a nucleophile can attack, because nucleophiles are electron rich and they will attack electron poor parts of the molecule. Another way that you can look at this is if you look at the ketone or aldehyde, what do we have here? We have an oxygen atom right here. So it is going to be pulling electron density towards itself via the inductive effect. And so what that does is puts a partial negative on the oxygen and a partial positive on the carbonyl carbon. And so when we analyze and look at our ketones and aldehydes, we can see electron poor areas on our molecule. And this is going to affect aldehydes and ketones reactivity. Now, what is the hybridization state of aldehydes and ketones? They're sp2 hybridized, right? So that means they're completely flat. So that means when a aldehyde, when a nucleophile comes in and attacks, how is it going to attack? Is it going to come in from the side? Well, why would it come in from the side when there's these big methyl groups that have steric bulk? And so it's going to get really hard for this nucleophile to come in from the side. But the ketone and aldehydes, they're flat. So what the approach of the nucleophile isn't going to be from the side. It's actually going to be coming from out of the plane, and it's going to come and hit this way. Or if I go around the board, it would come in and attack the other side. So this is flat, and it's going to attack on the outside or out of the plane side or in the board side and attack it that way. And then when that nucleophile attacks that carbonyl, what is it going to now look like? All right, so let's try to demonstrate this. Now we are on 2 dimensions here, so this is really difficult to, it's impossible to draw, but what I'm trying to show you is this nucleophile is out here, okay, where I'm at. And it's going to float around and attack from this angle. But I can't draw it that way, right? So I'm just going to draw it, the nucleophile coming in like this. And then we would have that. So the nucleophile is coming from outside of the board and attacking there. And so when it attacks like that, what do we have here? We're going to have the nucleophile came in from this direction. That's going to push one of the methyls back. And then we have the OH like that, or OH, the oxygen atom right there. So what have we gone? We have gone from sp2 hybridized now to a sp3 hybridized species. So what are we doing here? We are exchanging a pi bond for a sigma bond. So this pi bond, and we're exchanging it for this sigma bond right here between the nucleophile and the carbonyl. Well, that's no longer carbonyl carbon anymore, is it? To the carbon. When we take a ketone or aldehyde and treat it with a nucleophile, and we go from sp2 to an sp3 molecule like this, what the text refers to is that carbon right there is now a tetrahedral center. Now that tetrahedral center could be a stereocenter. It may not. In this particular case, it's not because we have the two methyl groups. But even if it's not a stereocenter, it would still would all of them, doesn't matter, would still be called a tetrahedral center. Okay? Now, when we take a look and compare an aldehyde versus a ketone, which one do you think would be more reactive towards a nucleophile? Now we're going to put on our Orgo 1 hats and think of some principles that we have been taught to answer that question. So would a nucleophile more readily attack an aldehyde or a ketone? So if we have here a aldehyde versus a ketone, which one is more reactive towards a nucleophile? Well, what do we have going on here? There's two effects generally when you're looking at reactivity. You can look at sterics and you can look at electronic effects. So let's focus on sterics first. So what's the difference between these two molecules? We have a one methyl group on the aldehyde and we have two methyl groups on the ketone. So you can see that there's more steric bulk on the ketone than the aldehyde because of that second methyl group. So that's really why an aldehyde is more reactive than a ketone, is because of sterics. It's just less bulky right here. So it's easier for that nucleophile. It's easier for that nucleophile to come and attack there than it would be to the ketone. So that's reason number one as to why aldehydes are more reactive. The second would be electronic effects. So if I take a look at the partial positive on this carbonyl, it's really, really big. Whereas the partial positive on this one is still there, just smaller in comparison to the aldehyde. Why would that be? Can you see what's happening here? We have alkyl groups. What do alkyl groups do? They donate electron density. But the ketone has what? Two electron donating groups. And because the ketone has two electron donating groups, it's going to make that carbonyl carbon less electronegative or less partially positive. And so it's going to be less reactive. So yeah, if you have, let's say, a nucleophile right here that's negatively charged, what is it going to be, which species is it going to gravitate to? Just based off of the concept of opposites attract. That's more positively charged, that's negative. It's going to gravitate towards this one compared to the ketone, just due to the charge difference. Okay. So now we're going to start looking at some other reactions that we have not seen before. And that's going to be the fun part. Now let's look at some reactions with aldehydes and ketones. So if we look at a generic reaction, looking at this ketone, we can have a nucleophile. And we can react it, and then we would get our, let's see here. Let's see, I will draw it like this. Yeah, draw it like that. And then after you do your nucleophile, you can do what actually happens is there's going to be a workup here that makes an alcohol. Okay? I'm not showing you the entire mechanism or the entire reaction here. But generally speaking, if you take a ketone or aldehyde, treat it with a nucleophile, you will generate an alcohol. So this alcohol right here is coming from this guy. You see the nucleophile there, and then the two methyls right here are right there. Generally speaking, that's what happens. But we have to consider now our nucleophile. There are some nucleophiles that are going to be strong. Strong nucleophiles typically have lone pairs on them and a negative charge. And so some examples would be, let's say, an alkoxide is a strong nucleophile. We have Grignard. Then I'm the world's worst speller. Grignards. And then we have hydrides. Those are all strong nucleophiles. And when you're under strong, or when you have a strong nucleophile, the reaction condition that this needs to be in needs to be under basic conditions. And the reason why this reaction has to be under basic conditions, because if you tried to take your nucleophile, which is negatively charged, and you want the nucleophile to react with the carbonyl carbon, but you have an acid present, the nucleophile is going to react with your acid before it's going to react with the carbonyl. So what's actually going to happen is your nucleophile is going to react with the acid and put on a hydrogen on the nucleophile, and then the reaction's done. So when you have a strong nucleophile, you have to use basic conditions. Now there's going to be some nucleophiles that are weak. And if the nucleophile is weak, then you don't use basic conditions. So if your nucleophile is weak, and generally you have a weak nucleophile when it's not charged. Negative charge, strong, neutral, weak. So you could look at just an alcohol. It has lone pairs, so it's still nucleophilic, but it is overall charge is neutral, so we consider it a weak nucleophile. And when you have weak nucleophiles, you don't use basic conditions, you need acidic conditions. And we're going to delve into the mechanisms shortly as to why this is the case. So as of right now, you just have to trust me that this is how it works. But in the next video, when we start drawing the mechanism, it will make more sense as to why this is the case. So we will stop here. This is a good introduction. And in the next video, we are going to start looking at generic mechanisms when you have a strong nucleophile versus a weak nucleophile.